Dear students, today we are going to start our fourth chapter in solid state physics, that is dielectric, ferroelectric and magnetic properties. First of all, what is a dielectric? Dielectric, it is a substance which is getting polarized in the presence of an external electric field. And in dielectrics, the atoms and molecules have closed or nearly closed electronic shells, and hence they represent another extreme limit of electron structure in contrast with the metals in which conduction electrons are free. So in metals these conduction electrons are free, but in the case of dielectric they have closed or nearly closed electronic shells. The electrons in dielectric material is tightly bound. So since the electrons in dielectric material is tightly bound to the atomic cores and are only slightly displaced from the equilibrium configuration by applying a fields of moderate strength. This is even more true for ions, and these small displacements are adequately described by a linear response theory in which the resulting electric dipole moment P is proportional to the strength of the electric field E. So that is already you have studied, that is when a dielectric is placed in the presence of an external electric field, this substance is getting polarized, and these that is in the presence of external electric field the substance is getting polarized, and the polarized means that substance possesses a particular electric dipole moment, and the electric dipole moment is produced is proportional to the applied electric field, and the relation between dipole moment and electric field is given by a linear response theory that we have already studied in our degree classes. That is P is proportional to alpha E, that is P is equal to alpha E, where alpha is the polarizability and P is the induced dipole moment and E is the applied electric field. And the dielectric polarization P is the vector sum of individual dipole moment and is defined per unit volume of molecules. We have defined the dielectric polarization as the vector sum of all the individual dipole moments. So individual dipole moment we have already expressed it as P is equal to alpha E, and dielectric polarization P is the vector sum of all the individual dipole moment per unit volume. So if there are n atoms per unit volume of these n atoms or molecules per meter cube or per volume, then the dielectric polarization P is equal to dielectric polarization P is given by n into P, that is n into small p, that is equal to n into alpha E, and this P is also related to applied electric field by susceptibility relation. So we have for linear dielectric we have that relation P is equal to epsilon 0 chi E into E. Therefore we can substitute these two expressions, P is equal to n alpha E and P is equal to epsilon 0 chi E, where chi it is the susceptibility, and then epsilon 0 is the permittivity of free space, etc. Therefore substituting these two or comparing these two equations, we get n alpha is equal to epsilon 0 chi E, or chi E is equal to n alpha divided by epsilon 0. And there is another scalar quantity which is called the electric displacement, and the electric displacement is given by epsilon 0 E plus P. So which can substitute the values here, that is equal to epsilon 0 E plus P is nothing but n alpha E, n alpha E. So we can take outside epsilon 0, suppose we take outside, so it will be equal to 1 plus n alpha divided by epsilon 0 into E. So this we can write it as 1 plus n alpha divided by epsilon 0, we can substitute it as by a constant epsilon r, where epsilon r is the relative dielectric constant. So comparing this equation, we will get epsilon r is equal to 1 plus n alpha epsilon, but n alpha by epsilon 0 we have already find out it as chi E. So d we can write it as d is either epsilon 0 epsilon r into E, or it is equal to epsilon 0 into 1 plus chi E into E. or chi E is equal to, we can write it as 1 epsilon r minus 1 is the classical equation. That is the classical equation which we obtain from these two expressions. Now, in the actual situation, this relation is valid only in gases in which we assume that the electric field we apply is the same as the field seen by atoms or molecules. So, when a field is applied to a particular substance, the field which we have applied will not as itself will be felt by the substance. In gases, it will be almost equal, but in solids and gas liquids, it is not valid. That is, in condensed matter, the atomic or molecular dipoles interact among themselves, and that is called a dipole-dipole interaction, and which produce internal electric field, so that the local electric field seen by a solid atom or liquid atom is different from the field which we have applied. So in the case of the solids and liquids, there will be dipole-dipole interaction, and because of this the field which we have applied will not be, or the field which you have local field experienced by the individual atom in the substance will be different from that we have applied externally. So the conclusion is that E local is not equal to E applied in the case of these condensed matters, and the local electric field has two contribution. The local electric field in the case of substance, we can have the contributions from mainly two parts. The first one is the macroscopic field due to the external field and the depolarization field. So the first one is the macroscopic field, which comprises of external field and the depolarizing field due to the charges generated on the surface of the dielectric. So the first part of this local electric field is the E microscopic. E microscopic is the it is sum of these external field and this depolarizing field. Depolarizing field means when a substance is when an external electric field is applied to a particular substance, a particular dielectric. Within that dielectric, there will be some other electric field is produced within the material, and this electric field will be in opposite direction to that of the applied field. So that is the depolarizing field. Now the second contribution to the local field is the contribution from internal field due to dipoles in the immediate surroundings of the point. So some field will be produced due to the dipoles in the immediate surroundings of the particular point. There will be contribution to the dipole moment. So the first case we can write it as E macroscopy is equal to E applied plus E depolarizing, where E depolarizing is always opposite to the E applied, so it is equal to E0 minus E1. Since E is microscopic is obtained by considering the medium as a continuous one in which the external field E0 is opposed by a depolarizing field E1 arising from the separation of charges by the external field. എക്സ്റ്റേണൽ ഫീൽഡ് കൊടുക്കുമ്പോൾ നമുക്കറിയാം എക്സ്റ്റേണൽ ഫീൽഡിനെ ഒപ്പോസ് ചെയ്യുന്ന രീതിയിലാണ് സബ്സ്റ്റൻസിൻ്റെ അകത്ത് വെദർ ഇറ്റ് ഈസ് പോളാർ ഡൈലക്ട്രിക് ആണെങ്കിലും നോൺ പോളാർ ഡൈലക്ട്രിക് ആണെങ്കിലും സബ്സ്റ്റൻസിൻ്റെ അകത്ത് പ്രൊഡ്യൂസ് ചെയ്യുന്ന ഇലക്ട്രിക് ഫീൽഡ് ദാറ്റ് വിൽ ബി ഓപ്പോസിറ്റ് ടു ദി അപ്ലൈഡ് ഇലക്ട്രിക് ഫീൽഡ്. So that is the first contribution to the local electric field. And the second part, which is due to the dipoles in the immediate surroundings of the point, which you have already said, and it is determined by considering a spherical cavity of radius of the order of dipole correlations around the point. So in order to calculate the second part of this contribution, we have taken a spherical cavity of the order of radius of the order of dipole correlations, such that the point which we are considering is within the spherical cavity. The internal field at the center of the sphere consists of two parts. So the second part is again consists of two parts. One is due to the charges on the surface of the spherical cavity. So we can divide these contributions into two parts. One is the contribution from the by the dipoles. The internal field at the center of the sphere will be of two parts. One is due to the charges on the surface on the surface of the cervical cavity, and the other is due to the dipoles within the cavity. So total second part, the second part of E local can be again divided into two, E2 and E3. E2 is because of the charges on the surface, and E3 is because of the charges within the cavity, and E2 is called the Lorentz field. So that is important. E2 is the Lorentz field, and for spherical cavity it is equal to P divided by 3 epsilon 0, where this P is the polarization vector. Here one P is omitted, that is where P is the polarization vector, and E3 can be shown to be equal to 0 for a spherical cavity in a cubic material. So out of E2 and E3, the contribution from E2 is taken as the Lorentz field, and the contribution from E3 is taken to be 0 for a spherical cavity. Now next we have to calculate the value of the Lorentz field. So in order to calculate the value of the Lorentz field, we have to calculate the Lorentz field E2 lined along the cavity wall in the direction of the applied field as shown in figure. So this external electric field is applied along the direction. Then we have to calculate this Lorentz field, that is because of the presence of the charges on the surface of the spherical cavity. This charge density arises from the bound charges and is determined by the normal component of polarization vector and is written as P is equal to P dot n. That is the surface charge density. ഇവിടുത്തെ ചാർജ് ഡെൻസിറ്റി ആയിട്ട് നമ്മൾ എടുക്കുന്നത് because it is because of the presence of the charges on the surface. Now the radial field intensity due to the circular ring of radius A is given by, so by the equation of the field due to a radial field intensity due to a circular ring we are considering. So in that case the expression for the electric field is 1 by 4 pi epsilon 0 dq into cos theta divided by a square, where we can see this is the area, this is the radius of the spherical cavity which we have taken, and this is the small area which we have taken, which is inclined at an angle theta. So this small area part we can take it as AD theta. This angle between this vector, radial vector, it is the angle is theta. Now substituting for different values, we have dq, we know it is equal to sigma into dA, that is a surface charge. Surface charge is equal to surface charge density into area. So this is equal to P cos theta into 2 pi a sin theta into dA is AD theta. So we can substitute the value, so we will get it as P into pi a square into 2 sin theta cos theta, we can take it as sin 2 theta d theta. So that is the value of dq here. So we can substitute the value of dq in this equation. So we will get this expression as dE2 is equal to 1 by 4 pi epsilon 0 into, for dq we have p into 2 pi a square into then here either you can express this as itself sin theta cos theta. So here it becomes multiplied by cos theta, it becomes sin theta into cos square theta divided by, and then in the new denominator we have a square into d theta. So by this we can take this p here, then 2 and 4 get cancelled, so it is pi and pi get cancelled, so p by 2 epsilon 0. Then this total field, this is E2, total electric field. E2 is nothing but the integral of this from 0 to pi, that is the that angle can vary from over the circle, it can vary over the ring, circular ring, this theta can vary from 0 to pi into cos square theta into sin theta d theta. So this is the expression for the total Lorentz field. Now in order to evaluate this integral, we have taken a substitution. We have cos theta is equal to x, then theta is equal to, for theta equal to 0, x is equal to cos 0, that is equal to 1, and when theta is equal to pi, x is equal to minus 1, because cos of pi is equal to minus 1. Then E2 will be equal to P by 2 epsilon 0 into integral minus 1 to 1 minus x square dx. Because since cos theta is equal to x, dx is equal to minus sin theta d theta. So it is minus 1 to 1 minus x square dx. By substituting, we will get minus p by 2 epsilon 0. Integral of x square is x cube by 3 within minus 1 to 1. So that is equal to minus p by 2 epsilon 0 into minus 1 by 3 minus 1 by 3. So that is minus 2 by 3. 2 and 2 get cancelled. So it will be equal to p minus p into minus 2. That is equal to p divided by 3 epsilon 0. So the expression for Lorentz field is nothing but p divided by 3 epsilon 0. Now substituting these values, we will get the total local field. The E local is equal to E macro plus E2. So it is E macro plus P divided by 3 epsilon 0. Then that is polarization vector P is equal to N alpha into E local. In that case, we have to substitute it as N alpha into E local in the case of condensed matters. So it is N alpha into E local becomes E micro plus P by 3 epsilon 0. And again here this P is again given by epsilon 0 chi into E macro for this type of dielectrics. Now from these two expressions we can substitute. So these two are the two expressions for P. So one is P is equal to N alpha E macro plus P by 3 epsilon 0, and the other one is P is equal to epsilon 0 chi into E macro. So by getting these two expressions, we will get on the left hand side we have epsilon 0 chi into E macro, that is equal to N alpha into E macro plus again P divided by 3 epsilon 0. Again for P you can substitute epsilon 0 chi E macro by 3 epsilon 0. So that is equal to, you can cancel E macro from all these. So epsilon 0 chi, that is equal to N alpha into 1 plus chi divided by 3. So epsilon 0 chi is equal to N alpha by 3. Suppose we take outside 3, then inside bracket we have 3 plus chi. Then epsilon 0 into chi, we have epsilon r minus 1. So that is equal to N alpha by 3 into 3 plus epsilon r minus 1. So 3 plus epsilon r minus 1 is equal to epsilon r plus 2. So epsilon r minus 1 divided by epsilon r plus 2, that is equal to N alpha divided by 3 into epsilon 0. So this equation is called, this equation also you have already studied, which is called the Closius-Mosotty equation. And since epsilon r is equal to n square, the refractive index of the substance, then this Closius-Mosotty equation can also be expressed as n square minus 1 divided by n square plus 2 is equal to n alpha divided by 3 epsilon 0. So this is the Closius-Mosotty equation in the case of dielectrics. Okay, so here we can stop the first video of this dielectric.